So, hello everybody, I am Lara, it's Theatre of Science, it's the third lesson of materials. So the first lesson we learned about all the words, basically lots of different words that you use to describe materials like metal, plastic, fabric, wood. Last lesson we looked at plastic, this lesson we're looking at metals. So what is a metal? It's actually quite a complicated question, but it's it wouldn't be a very good lesson if we didn't touch on it. So very, very basic, fast, what is metals answer, okay? Have you seen the periodic table? Here it is. There's a periodic table, isn't it a thing of beauty? So the periodic table is a list of all the different atoms in the whole world, right? It's a list of all the atoms in the world. What is an atom? I know some of you have seen this a lot, but we've got to do it again. It's important. So an atom is, very simply, is positive particles with tiny little negative particles whizzing around the outside, okay? That's really all you need to know for this lesson, is that an atom is little particles that are positive with small particles that are negative whizzing around the outside, okay? And if you can get, and the different kinds of atoms, like the number of positive particles in the middle makes different atoms, okay? So you could get like a carbon atom, and you could get an oxygen atom, and you could get a nitrogen atom. And things that exist as one atom are called elements, all right? So the periodic table is a list of all the elements. It's a list of all the single atoms you can get. So like carbon is an element because it exists as just one atom. Oxygen is an element, it exists as just one atom. Carbon dioxide, which you hear people talking about a lot. Carbon dioxide is not an element because it's two atoms bonded together, okay? So two atoms bonded together, not an element. Elements, single atoms, okay. So let's have another look at this periodic table of elements, like single atoms. So many of them are metals, like most of them are metals. Look, so you can see here that the red ones are called alkali metals. The orange ones are actually called alkali earth metals. The yellow ones are transition metals. The green ones are base metals. Even these blue ones are semi-metals. There's so many metals. And finally over here you get to things that aren't metals, right? So in chemistry, not a chemist, the definition of a metal is, like, again, very basically, that it's a particle that quite easily loses its negative particles and becomes positive, all right? So when it bonds to stuff, it becomes positive, sort of one chemistry version of a metal. I'm a physics teacher, and really when we talk about metals in physics, we just say they're things that are like shiny and hard, yeah, and generally grey. So that's all I'm going to say about what a metal is, but that might come up in a bit. Okay, so I asked you at the start about precious metals. What is the big deal? Some metals we just use day to day, and some metals are super precious and special. Like we talk about gold all the time. What is it about gold that makes it so great? Now, probably, if you were paying attention, you would like chatting your ideas out loud to yourself or to someone else, you might have said things like they're rare. And you would be correct. But there are other reasons. I'm going to give you 10 seconds, look at all these reasons and tell me what makes some precious metals so valuable. Is it because they're rare? They don't react with other substances? Is it because they're beautiful? Is that a reason for things to be expensive? Do they not corrode easily, like break down? So something rusting would be something corroding. Do we love them because they're very reflective? Are precious metals precious because electricity passes through them easily? Or is it because they're hard to make pure? They're very sort of similar to rare, I suppose, isn't it? They're difficult to get on their own. Well, 5 seconds. Which ones is it? One. The answer is, you're absolutely right if you said precious metals tend to be rare. Also, they don't react with the substances. They don't corrode easily. It's all of them. Okay. The reason that gold is so precious is partly because it's rare, but it's nowhere near the rarest metal. The reason that we use gold for coins is because it's just got this amazing combination of properties. It doesn't react well with other substances, which is good because you don't want, if it was like carbon, you might reach into your wallet and find that it had all turned into carbon dioxide. That would not be good. It is very beautiful, and we like that. I'm going to flip you for a second, right? Gold is the only metal which is golden, right? And stays golden. So you can lock gold away in an Egyptian tomb for 1,000 years, you get it back out, it's still beautiful and golden. If you've ever been to a city and seen a beautiful like church with a green roof, that's copper. So copper starts out beautiful and goldeny, but it reacts quite easily with the oxygen to go, still beautiful, but very different green colour. So gold's the only one that doesn't do that. That's why we love it for jewellery. But it also doesn't corrode easily, so yeah, it's great. That's why we use it for coins. There is a very precious metal called rhodium, which is very reflective, gets used for mirrors. Silver allows electricity to pass through it the best. More about that later. So there's all kinds of reasons why metals could be precious. I'm going to start the lesson by focusing on this one. They are hard to make pure. How do you extract metal out of whatever rock it happens to be in, okay? So just relax a little bit. I'm going to tell you the surprisingly interesting yet tragic story of aluminium. There's more aluminium in Earth's crust than any other metal. It is the most common metal in Earth's crust, but it's not pure, okay? It's always mixed up with other things. So scientists suspected that this stuff called alum had an unknown metal in it as early as 1787, but we couldn't get it out. We didn't have a way to extract it, take it out, until 1825. When we finally managed to do that, we didn't get much of it, right? So it was rare. So this is a kilogram bag of flour, but pretend it's aluminium, for visualization, right? How much do you think, when we finally managed to extract a little bit of aluminium out of alum, how much did it cost? Like a kilogram of aluminium? It was about £1,000 in today's money. Aluminium was so super rare that it was more valuable than gold. In fact, Napoleon III had some aluminium knives and forks set aside for the most important guests at the banquets. It was so posh, the lesser guests had to just have the golden cutlery. Aluminium was the bestest of the best. But in 1854, just getting ready for the accent, Henri Etienne Saint-Clair Deville, a French chemist, he found a new, better extraction method. What does this mean? Well, it means we've got more aluminium suddenly, so it's not as rare, so the price goes down. So now the cost of 1 kilogram bag of aluminium is £30 per kilogram. That's a drop of 97% in 5 years. In 1889, Charles Martin Hall basically sort of puts aluminium with a liquid in a bath and puts an electric current through it, and that's a very good way of separating out aluminium, and suddenly it only costs 97p per kilogram. By 1914, aluminium was so easy to extract that the price had fallen to 25p a kilogram. Picture of some foil wrapping up a manky sandwich saying, no! How weird is that? Maybe you've brought some aluminium foil with you because we're about to do an activity with it. It's so weird and absolutely true that this stuff used to be like prized by kings, and now we're just like, just peel it off my Easter egg, chuck it in the recycling if you're lucky. Right, let's do an activity with aluminium. It's sort of a bit crafty, and while we're doing the crafting, I'll tell you more about it. Okay, so what you're eventually going to do, please, is have a strip, like about the size and width of a lolly stick, that's got a foil on one side and paper on the other side. That is what we're aiming for here, okay? So confident people can plough ahead, but you've got to make sure that there's no flappy bits, all right? You want to make sure the foil is really well stuck to the paper. So what we need to do, I think the best method is, if you've got paper that is slightly bigger than your foil, just whack glue all over your bit of paper and then stick the foil to it, and then we'll cut it out so that the edges are nice and clean, okay? So I'm going to put glue all over my paper. Yeah, so my first fascinating aluminium fact is, you know how one side of aluminium foil, if you've got some clean stuff with you, you might notice, one side is really shiny and the other side is much duller. What's that about? Well, I know now. It's because they roll it out so thinly in the factories that they can't roll it out as only one sheet or it'll break. Right, I've just put glue on a piece of paper, that's all that is. So they have to double it up to put it through the rollers, right? And then they peel it off later to put it on rolls. But so because they double it up, the sides that are facing the rollers go really shiny, and the sides that are facing each other, they're dull. So it's just an accident. You don't need to use like one side for one bit or one side for the other bit. There you go. Right. So now I'm going to stick my foil to my paper and give it a good smooth. So aluminium it's a metal, right? It's a classic metal. So it's shiny. It is, if you came to the first lesson, it's ductile. You can draw it out into wires, right? You can roll it out into sheets. It's malleable, which is still my favourite word in materials. It's squishy, yeah? It's malleable. If you squish it, it stays squished, which is incredible, really, when you think about it. And some other things, but we'll do the activity to talk about the other things. Okay, so now I've got foil stuck to a piece of paper. I'm going to cut this out. See, so now we haven't got any flappy bits, see, hopefully. And now you can cut out your lollipop stick style strips. I think thinner is better. Go thinner, if in doubt. Yeah, about that thin. So aluminium is actually quite unusual because what you're holding, if you're holding some aluminium foil, is pretty much pure aluminium. Now, I say pretty much because in that little story time, I said that it's not found in its pure form in the ground. This is because it is very reactive. Okay, here we go. Got some little, so that's what you do. You could do that now while I finish off chatting. Yeah, it's really reactive. So you don't find like nuggets of aluminium in the ground the same way you might find little nuggets of gold. So the top layer actually of your aluminium foil is aluminium oxide. The top layer of aluminium atoms of the foil have reacted with the oxygen in the air to make a thin layer of aluminium oxide. You can't tell, can you? I guess if you scratched it with a really sharp knife, then you might reveal some pure aluminium, which would instantly oxidize, react with the oxygen in the air again, and form aluminium oxide. But generally speaking, it's pure. They don't mess around with it. It's just useful as it is. Right, shall we start the activity? I cannot overemphasize this enough. Have a glass of water with you, okay? Because we're going to light a candle now and hold these strips over the candle. There's a very high chance that the paper will set on fire. I mean, you know, not if you're careful and you hold it over far enough away, but, you know, mistakes were made by me in practice. Here we go, so I'm going to light my candle. You can do this too with my ludicrous extra long matches that I got tricked into buying in Sainsbury's. Just said, do you want a big box? I thought he meant, do you want a lot of matches? Not, do you want a small amount of massive matches? Why would anyone want matches? It's big. I know, for barbecues. I live in Yorkshire. I have 2 barbecues a year if I'm lucky. Anyway, sorry, just filling time. Here we go. So you've got your candle lit. Now, we are going to hold your aluminium and paper strip over the flame from a distance. Wait, I'll do it with you and see what happens. But really, for good science, we should do like a control first. So first of all, you don't have to do this, you can just watch. I've just got a piece of aluminium foil that I'm going to hold over the flame, and we can observe what happens to that first, okay? Here with me. Okay, so here's the flame, here's the foil. I'm going to hold one above the other, and you can predict what's going to happen if you like. Do that now. All right, let's see if you were right. Can you see that? What is happening? What do you observe? I'll turn it over. Sometimes in science, the correct answer is nothing. Nothing at all. Are we happy that nothing is happening? No? Zip. All right, now I'll do the same thing with just a piece of paper. Again, you don't have to do this. In fact, I don't recommend that you do. But I'll do it so that you can see what happens. So, just paper. Still nothing, except it's going a little bit brown, okay? Nothing else. Right, get your strips then. Or you can just watch me, obviously. Get your little strips. What should we do first? Let's hold the strip foil side up. No, foil side down. Let's put it foil side down over the candle, okay? Hold your strip, foil side down, so the foil side is facing the flame, and see what happens. The tension. What do you think is going to happen? Let's just do it. Ooh, can you see that? Palpable curling. Did it curl upwards? Do you believe me? I'll do it again. It's curling upwards, right? Definitely curling upwards. A huge amount of curling is occurring. brilliant. Like I say, I've got loads of these strips left. This is my kid's Easter egg wrapper. I'm just going to do a couple more. So we're absolutely sure that it definitely curls upwards. Why did that happen? Oh, brilliant. Right. Why has that happened? Well, because I do this lesson on Facebook first and I get some comments, I know some of the things that you might say. And someone yesterday in the lesson made the brilliant observation of, oh, well, heat rises. So maybe the candle is heating the air and the air is moving upwards. And that's what's pushing the foil and the paper upwards, right? Which is pretty good, isn't it? But how do we know that that's not what's happening? That can't be what's happening, can it? It's not just that the hot air around the candle is pushing up the strip. How do we know that? Because it didn't happen when we just held paper over, and it didn't happen when we just held foil over. So it doesn't make any sense. Like, those things are lighter. Why wouldn't they go up? The other way we can prove that's not what's happening is by doing that activity again, but this time holding the foil strip so that it's facing the flame. Let's do that. Yeah. What do you think's going to happen? Oh wait, I just did this one, didn't I? Okay, sorry. Paper facing downwards, paper facing downwards. This is why I need comments, because I'm sure you were all shouting at the screen then. Paper facing downwards. Just move this up a bit so we can see. Paper facing downwards. Don't hold it too far above the candle, and definitely have a glass of water handy. Bless you. And did you see that? I'll do it again. Paper facing downwards. Oh, it's curling down, right? It's definitely curling down. I saw Hannah and Abby put a very good Instagram post up after yesterday's lesson of them doing both at the same time, which was very cool. Whoa, whoa, whoa. Don't chat in science, Lara. Don't chat in science. But I've only got one hand. Yeah, it definitely goes downwards, right? Have you noticed that? You can have a little fiddle with that at home if you've got an adult with you. I'm going to quit while I'm ahead and blow this candle out while still nothing is on fire. Why did that happen? Why? Well, why? Yesterday, people were saying things like, oh, the metal was pushing on the paper. That's a good answer. But why was the metal pushing on the paper? Why isn't the paper pushing on the metal? Some people were saying, oh, well, the metal is getting bigger because it's hot, like things expand when they get hot. So the metal expanded when it got hot, and that's why it pushed on the paper. But why does the metal get bigger and the paper not get bigger? Well, it's a good job we're doing a metals lesson, isn't it? So we can talk about what's happening inside the metal now. So last week we looked at plastic, and paper is similar to plastic. The particles, a chemist wouldn't like this, but the particles are kind of like mushed up, right? They're all like wiggly. So in plastic, we looked at how all the atoms are joined up in very long strings, like hundreds or thousands or tens of thousands of atoms all in long strings. The inside of plastic looks like sort of a cold bowl of spaghetti with everything all mixed together. Metals, oh, they're so much more organised. Metals, the particles inside metals, you know I said that atoms have positive particles and negative particles. Inside a metal, the positive particles are all beautifully lined up, like this. Kind of like how you see fruits in a grocer's shop, yeah? And they're so beautifully lined up that the little negative particles, the electrons, they're just free to whiz around them. They're just sharing the electrons. It's called free electrons. So the electrons are just like, hey, all the negative particles moving around in between the metals. This is an incredibly beautiful thing, because actually what electricity is just little charged particles moving. So this is why it's really easy for electricity to move through metals, because they've got free electrons that just carry, I mean, they are the electricity, they don't carry the electricity, that's what they are. Whereas obviously in plastics and paper and other products where the particles are a bit more sort of mixed up, it's much harder for that electricity to travel. It's also very easy for heat to travel. Heat travels in a similar way to electricity. So it's very easy. You probably know this. You've ever been like to a campfire and you've had a metal stick to toast a marshmallow. Your hand starts burning, right? That's why we use wood to toast marshmallows, because heat will travel very easily through the metal into your hand from the fire. So heat and electricity travel well through metals. I'll give you the physics word for this. It's called conduction. That's a weird clown. So metal, I always have like a proper teacher moment when my pen runs out on screen. It's like, you just never feel more like a teacher than when your pen runs out live in front of a class. They're good conductors, that's what we say. Good conductors of heat or good conductors of electricity. Metals are good conductors. Oh, I've written it backwards. I can hear you all screaming at the screen. It's because on Facebook I have to write backwards. And also because, weirdly, YouTube shows me it backwards. So to me, that looked right. They're good conductors. Whereas plastics, paper are bad conductors. So that's one of the things that's happening. The other thing that's happening is when you heat up metals, or indeed anything, the particles vibrate more. So when you heat up a metal, the particles vibrate more and they spread out. And obviously, yeah, metals very well organised. So when they spread out, the particles, they do expand very nicely. The paper is also expanding. The particles are moving further apart, but not as easily. So the reason why your paper bends when it gets hot is two reasons. One of the reasons is that the metal side is expanding more than the paper side, and that is pushing. And the other reason is that the heat travels much more easily through the metal than it does through the paper. Like again, someone yesterday said a very clever thing like, why does the paper burn but the metal not burn? The reason is that the heat carries through the metal, like travels through the metal, so it sort of spreads out the energy, whereas the paper can't do that, so just bits of it burn, right? Oh, that's a lot, wasn't it? If you were here, I'd make you chat, but you know, what are you going to do? Right, so moving on then, I said that aluminium was quite rare because it's in its pure form. Look around your room right now. Have a look and see how many different kinds of metals you can see. We did this last week with plastic. Might be a bit hard with metals. Just have a look around your room. How many different uses of metals can you see? I've got a door hook. I've got some handles on my filing cabinet. I've got a globe. How many different metals can you see? They are probably, almost certainly not, pure metals. What do you call metal that's got other stuff mixed into it? I'm glad you asked. It's called an alloy. So the last bit of the lesson, an alloy is, I'm just going to have to, you say it wrong if you don't say it like this. We'll just have to say the chemistry GCSE way of saying it. An alloy is a mixture of two or more elements where at least one of the elements is a metal. It's complicated to say, isn't it? But it's easy, really. It's an alloy is a metal mixed with other things. And the other things you mix them with could be metals, or they could not be metals. Like steel, for example, is metal, iron, which is a metal, with a little bit of carbon in it. And carbon is not a metal. So steel is an alloy of iron, a metal, and something else that isn't a metal, another element, right? You getting this? Sometimes I talk too much and it confuses things. Just do this sheet for me, okay? Super simple, just a 10-second question. How have you understood what an alloy is? An alloy is a mixture of two or more elements, like atoms, yeah, from the periodic table, where at least one of the elements is a metal. So I've got 5 descriptions here. Can you just tell me which one of these is not describing an alloy? A metal and 2 non-metals mixed together. Is that an alloy? A liquid made of 2 metals. Is that an alloy? 2 metals mixed together. Alloy? 3 metals mixed together? Is it an alloy? A solid made of 2 non-metals? Is that an alloy? Like 5 seconds, just tell me which one of those is not describing an alloy. 3, 2, 1. Yes, well done. It was a solid made of 2 non-metals. An alloy has got to have a metal in it. I thought the liquid one might trick you, but there's no mention of whether it's liquid or solid or gas, is it, in the description? You do get alloys that are liquid. But yeah, if it was just 2 non-metals mixed together, it wouldn't be an alloy. Other thing to quickly note is that it has to be sort of useful. Like it has to be that we've made it to kind of make a metal better. Like I said that your aluminium foil had a layer of aluminium and oxygen on it, aluminium oxide. Aluminium oxide is not an alloy. It is a mixture of a metal, aluminium, and a non-metal, oxygen, but it's not useful. It doesn't have any like useful properties. It's not an alloy, okay? Shush. I'm going to show you some pictures now of what alloys are and what they're used for and some descriptions, and I want you to match them up. This is going to give you an idea of why alloys are brilliant. Yeah, I'm not going to say any more. Just look at this sheet, okay? Here we go. So these are 4 uses of alloys, 4 handy alloys. Some of them you might have heard of. So bronze is an alloy. It's copper, a metal, with a little bit of zinc, a metal, and tin, a metal in it. So bronze, copper, zinc, and tin all together. It can change shape very easily. It doesn't corrode, like doesn't go rusty, and it also kills germs. I couldn't believe this, but that is true. It's got antimicrobial properties, like it doesn't go mouldy. Duralumin is aluminium, a metal, and copper, a metal, mixed together, which makes it very light, not dense, but very strong. What would that be good for? Brass is copper and zinc. Electricity flows very easily through it and it's very strong. And stainless steel is iron with a bit of chromium in it, among other things. It's very strong, it doesn't rust, and it's not damaged by acids. So which ones of those would you use to make plug pins, like the bits on the end of a plug that get stuck in a wall, 2p coins, knives and forks, and aeroplane parts? Which alloy goes with which use? And second question, a bit harder. Cast iron is an alloy used for making large frying pans. What do you think cast iron would have to be like to make it good at this job? So you're using cast iron, it's an alloy, you're making a frying pan. Why are you doing that? What is it about cast iron that makes it good at being a frying pan? I was going to give you, I don't know, what do you think? 30 seconds, because the cast iron one's a bit tricky. You might want to write some stuff down. If you get bored, you can always subscribe to my Facebook. No, not my Facebook page. Subscribe to my YouTube channel, or go over to my Facebook page and write me some nice comments on my post. I am really bad at staying quiet. 10 seconds of total silence so that you can finish those questions. Okay, I'm bored now. Let's do this. Bronze is good for coins. If you've got a 2p coin on you, then keep it around. I'll talk about it in a minute. It kills germs. I mean, how handy is that? Not that coins don't have any germs on them, but probably fewer germs than other metals. And obviously coins don't go mouldy, which is good. Duralumin, it's aluminium and copper mixed together, so that makes it very light. Obviously you don't want things that you're going to put on an aeroplane to be super heavy, but it also keeps its strength. It's amazing. It's just total genius. Brass is copper and zinc mixed together. So electricity flows through it very easily, but it's also strong. So that's good for plug pins. Flip you ever so slightly. No, I won't. No, I'll do the answers and then I'll flip you. And stainless steel, it's very strong, it doesn't rust, and it's not damaged by acids. So that's good for knives and forks. And the answer that I got for the cast iron one is that the reason you mix cast iron with other things is because it can be poured into different shapes, and crucially it doesn't rust, and also it doesn't melt easily, which is a useful thing for a pan, isn't it? And it doesn't react with other things either. It doesn't react with like water. I suppose that's what rusting means. Right, flipping you around. You okay? You got all that? It's YouTube, innit? You can always come back, take a screenshot right now. Take a screenshot. That's what you should do if I'm rushing you. There we go. I'll flip you. The plug pin one I think is really interesting. Copper is brilliant at allowing electricity to pass through it, okay? Copper wires are in all sorts of things, but copper is very soft. So you don't want to make the pins of a plug out of copper, because if you're repeatedly, don't play with electricity, but you know, when it keeps getting mashed into a wall, the copper pins would very easily get damaged. So you mix a tiny little bit of zinc in with the copper, and it still allows electricity to flow very well, but it makes it super strong. It's so clever. I'm so excited. I used to think that alloys were boring, and now I'm like wildly excited about them. Stainless steel is another really good one, right? So stainless steel, if you've got a spoon or a fork with you, that will be made of stainless steel. It's mainly iron, but iron goes rusty really easily. You ever been outside and seen an iron nail? It will have rust on it, right? You don't want stuff that you wash every day and put in your mouth to go rusty. So you add a little bit of chromium and some other stuff, and it doesn't go rusty anymore, but it's still really strong. So you can eat with it and it doesn't bend. It's just very clever. Someone was asking me yesterday why coins taste weird when you lick them. And although I've never licked a coin, and nor should you, I kind of knew what he meant, yeah? I guess that's because the metal on coins, like bronze, is slightly more reactive. I'm guessing, I didn't look it up, but steel, not very reactive. So you don't put a fork in your mouth and be like, everything tastes of metal, do you? That wouldn't be useful. Yeah, and cast iron, well, you melt iron down, you add other stuff, like carbon, and then you can cast it into all different shapes. It's actually very brittle. It breaks quite easily, but it can get very hot without melting, and also it doesn't rust. Again, very useful. Got us through the Iron Age. Okay, I think that's pretty much it, except to say, again, just geeking out, if you've got a 2p or a 1p coin, then before 1992, that coin would have been 97% copper and just a little bit of zinc and a little bit of tin. But then in 1992, copper suddenly became really valuable. Like, we needed more of it, yeah? So I suppose that sort of means it was rarer because we needed more of it, it got more expensive. And it got to the point where 1p made of copper, if you'd melted it down and just got the copper, that would have been worth more than 1p, which is a bit confusing and doesn't work for coins. So now, after 1992, what they did was they made it 94% steel, like we've looked at, hard, like iron alloy, and just coated it in a tiny bit of copper. So it's only 6% copper now. It's quite interesting. We still call this stuff tin foil. It's not tin. Tin ended up making the food taste quite tinny, so we changed it to aluminium. Also, aluminium was dirt cheap. And if you brought a tin can with you, they are also not made of tin. Never have been. When they were first invented, they were made of iron, but iron goes rusty, reacts with food, not cool. So now we tend to make them out of aluminium because you can just punch an aluminium sheet into the shape of a can and put a lid on. It's much easier to make in a factory, so cheaper. Or sometimes they do make them out of steel. But if you've got an acidic food like tomatoes, they probably have still lined the can with something to stop it reacting with the metal. So sometimes they line them with tin, which is why they're called tin cans. But these days they're probably more likely to be lined with a lacquer. Right, and thus ends my lecture about the metals around us and what they are used for. Shall I do my ad very quickly? So I want to show off my magazine. And then I'll give you some summary questions and GCSE questions so you can see how well you've understood. So, if you would like to support me, if you're enjoying these lessons, I do one every week during term time, and I do a show every week as well. So actually, at 11:30 today, I'm going to do the YouTube lesson show on wolves. That's where I don't really ask you any difficult questions. I mean, I'm going to today. There's a Lego story time. I'm getting distracted. If you support me with £5 or £6 a month, I will send you the Job Science magazine. I'm so proud of it. This is the rainforest one. I've got a couple left and I'm not quite ready to send out the new one. So if you sign up today, I will send you this in the post, along with some rainbow glasses, which make you see rainbows. They're amazing. And a description of how they work. But Theatre of Science magazine is designed by my husband and written by me. It's got bug craft in it. It's got a choose your own adventure. Will you die in the rainforest? Some of you did. It's got a beautiful comic in it that my husband illustrated about a famous insect expert who went off to visit some cannibal tribes. But the latest one, which you are going to get quite soon, it's in envelopes in my living room, is on mould. I'm going to send you a biodegradable plastic bag so you can grow mould like I did. It was so fun. There's another choose your own adventure. Will you get fired from your new job in a museum? And there's another comic about the only woman to have a Nobel Prize for Science who is British. Who knew? Right, GCSE questions. Thank you for sitting through that. Yeah, there's a link on my YouTube channel. There's a link to Coffee. That's the website you want to go to, Coffee, to send me £5 or £6 a month. Get nice things. Thank you. Right, your questions. So I actually think the GCSE questions are slightly easier than the summary questions today. You can answer in as much or as little detail as you like for this. The summary questions, have you understood today's lesson? Can you explain in a few words why aluminium used to be very expensive but is now very cheap? Why did aluminium used to be super expensive but is now cheap? As much detail as you like. And copper lets electricity flow through it but is not very strong. Explain why it is mixed with zinc for use in plugs. Why do we mix zinc with copper when we use it in plugs? And your GCSE questions. What is an alloy? Oh, this is a memory game, this, isn't it? What is an alloy? It's 2 marks, so you might get 1. And 2, for 3 marks, name an alloy. Explain why the alloy is useful, like what properties does the alloy have, like I know, strong or hard or whatever, and give an example of it being used. So that's for 3 marks. It's a good example, it's a good exercise in resilience, this. So even if you're like, I can't remember what alloy is there, you might be able to name one and then get a mark at GCSE. Should be cool. All right, I'm going to hold my breath and be totally silent for a whole 30 seconds to let you write the answers to these. I'll go and get a coffee and then I'll have to be quiet. Get a coffee. You've got until I've poured my coffee and come back to answer these questions. Trying to walk slowly because I want some details in these answers. Right, here we go then. You ready? What is an alloy? Oh, well, if you were actually doing this for GCSE, I'd have probably just made you learn it parrot fashion, depressingly. An alloy is a mixture of two or more elements where at least one of the elements is a metal. Whew. I think if it was GCSE, you'd probably have to say the word element and not like stuff or things. But if you've said that it's a mixture, give yourself a mark. And if you've said that at least one of the things is the element is a metal, give yourself another mark. I'll leave it up to you how generous you're feeling. Name an alloy, explain what it's used for, and give an example. So you could have had bronze, which is what's used for coins, because it kills germs, you could have said, or it doesn't corrode, doesn't rust easily. Well done if you got duralumin, which is, you could have said light or strong. Well done if you put both, which is used for aeroplanes. Well done if you said brass. I don't know if they're hard to remember, aren't they? There's not actually that much difference between bronze and brass these days because it's good at conducting electricity or it's strong. The one that I'd probably put down that I would remember is stainless steel is used to make knives and forks because it doesn't rust. But anything else you thought of, you want to chat about pewter, that's absolutely fine. Give yourself a mark. Summary questions. Aluminium used to be cheap, expensive, but now it's cheap because it used to be very hard to extract, so it was rare. Now it's easier to get, so we've got plenty of it, so it's cheap. So well done if you got the idea that it used to be difficult to get it, and now it's easy. So because it's very easy to get, it's cheap. Copper lets electricity flow through it, but it's not very strong. Why do we mix it with zinc before we use it in plugs? This is quite a good example of why GCSE questions are different to other questions. Obviously, this wasn't a GCSE question. Well done if you've put just to make it stronger. But to give a bit more detail, you'd have to say why it needed to be strong. So it's mixed with zinc to make it stronger, but the reason it needs to be stronger is because plug pins have to be strong so they don't bend when they go into the wall. All right? Whew. And that is the end of the lesson. Well done. I'll just hang on there a minute so that you can write some answers down. And then I'd better go because I'm doing the Wolf Show in about 15 minutes on YouTube. Because I had to take my daughter to the dentist yesterday. And I've got to set up story time. Here we go. I'm just putting together the jungles of India as you look at those answers. Okay, flipping you around. Good. Right, you lot. Thank you so much for coming. We've only got 2 more materials lessons left. And we need to do wood and fabric. And like reuse, recycle and all that stuff. Oh, a new coffee member. Thank you so much. Ah, well, my day is made. That's so lovely. Thank you very much, person who just joined me on coffee. I will be going to post off your things later. Yeah, thanks a lot for coming. I might see you for Antarctica show at the weekend. So Saturday morning, Monday and Wednesday at 9:30 on YouTube, like the same as this. I'm going to do the science show, a little Lego story time about Antarctica. For that, if you're going to come, I'm so sorry, I just keep talking, but if you're going to come to my Antarctica show at the weekend or next week, you need to have prepared in advance an empty food can that you filled with water, like, I don't know, about 2/3, halfway full with water, and put some salt in it and stir it and put it in the freezer. All right, empty food can, water, salt, stir, put it in the freezer. I still haven't done it. I'm going to forget. We're going to make frost. It's such a cool activity, but the water needs to be frozen. So you need to do it now. Go away and do that now, and I'll see you at the weekend. All right, thanks for coming. I'll see you.